and start recording here, and then I'm gonna actually try using. So we had issues with the latency. We had issues with the latency before, so I'm gonna try actually just going live on here and see if that works any better. So I think you can like double click on me to be able to see what my screen has. And you should hopefully see a Kahoot, which is what we're going to get started with. So as long as you can see that, go ahead and pull it up and enter the PIN, log in. I'm just going to do a little tiny bit of review here just to remember where we're at and make sure we're good to go moving on.
So the latency is a lot better than OS was with YouTube last week.
Okay, cool. Yeah, I tested it here, but I wasn't sure if I mean, I highly doubt it's doing something smart like this, but I was testing it with a computer right next to this, so I wasn't sure if there's anything like, just pinging back and forth between the two computers instead. But yeah, hopefully it's better.
Right. Yeah, it's definitely awesome. A lot better.
Okay.
I don't know, are the others looking for YouTube? Because I don't know if they're...
Yeah, hopefully not. I
manually
should have
on
probably sent out
Discord.
something in advance.
We sent out maybe a just quick email in case people are looking. People usually check those.
Can anybody hear me?
Yes.
Yep.
You said you're sending out an email, Rupam?
I can do that, yeah.
Thanks.
Let's see. EC486.
I think we're missing. I don't know who Saul Bloom is. Did I get a Kahoot name for them?
I'm random user.
Okay.
Eugene.
Okay, cool. So we're missing Fish and Mike. Young Mike. Not old Mike. Okay, we will get started with this, and then we'll see if the other two join later on, or if they're just watching the recording. So let's get started. So first up, which of these tasks is the front end of the compiler primarily responsible for?
Oh boy, it's been a while.
Yeah, nice. Yeah, so it's responsible for both of those tasks, syntax checking and parsing. It's not really responsible for optimization, and it's definitely not responsible for register allocation. So nice work. Random user was the fastest. Good job. Next up, which of these tasks is the back end of the compiler primarily responsible for?
Hey, did that email go through? I don't know if I sent it to the right one. Totally a
See it.
show that. Okay, cool.
Oh no.
RIP.
Okay. So the back end of the compiler, is mostly going to be responsible for. Sorry, I'm clicking on the wrong thing here. It's mostly going to be responsible for register allocation and instruction scheduling. It's a little bit responsible for optimization, but the primary function is these couple last steps. Optimization is usually the sort of middle part of the compiler that handles that, which is what we're going to be talking about today. I do want you to keep in mind register allocation and instruction scheduling, though, because these are things that we're going to refer to quite a bit, and I know we haven't covered exactly what they are, but we're going to sort of look forward, at these two topics, because a lot of the optimizations that we do in the middle part of the compiler affect the efficiency of register allocation and instruction scheduling once we get to the back end. So, if we have more scope to schedule instructions because we did some optimization in the middle part of the compiler, that can make instruction scheduling easier. If we have more things, though, that we have to fit into registers, that can make register allocation harder. So we're going to kind of talk about those two, sort of looking forward to the back end without really talking about the back end yet. Okay, Saul Bloom jumping up into the lead. Next up, what IR format does the optimizer operate on? Okay, cool. So yeah, the optimizer is operating on SSA form for the most part. We do a little tiny bit of optimization, probably going from the AST to SSA form, but not a lot. So it's mostly just SSA that we're working with. Random user back into the lead. Okay, next up, what type of LLVM IR instruction would be associated with the statement int x equals star p, where p is a pointer? Okay, nice. Yeah, so either one of those two is correct. So we are loading something from P, since P is on the right-hand side of this equation. That means we're loading something from it, putting it into the memory in X. And since X is an integer that's on the stack, that could also be an alloca instruction that we would have associated with this piece of code. Call instruction would be like calling a function, so we probably wouldn't see one of those here. Okay, neck and neck. A couple more. True or false? Instructions are values in LLVMIR. Nice. Yes, that is correct. That is one of the main points of LLVMIR, is that we use these instructions as values into the next instruction. Sorry, by the way, if you can, I don't know if you can hear the dogs getting a drink. Unfortunately, they are here with me, and my wife's not home to keep them away, so there may be some minor sound disturbance. True or false? In SSA form, each value is defined and used only once. Okay, a little bit of a trick question here. So defined once, true. Used once, false. So we can use an SSA form value any number of times that we want to use it. The only condition here is that we only define it once, so that way we can track back that value to its current definition. So we can use these more than once. Okay, and final question. True or false? Each basic block has a single entry and single exit. Okay, nice. Yeah, that's the definition of a basic block. Great work. Okay, so let's see. Third place. Nice work. Second place, and I'm going to say, I guess, that Eugene edged out Mike for the win here. So nice work, everyone. Hopefully that sort of jogs your memory a little bit after, over 2 weeks of not having class. And we can dive back into to the notes. So today we're going to be talking about optimization. So this is the sort of middle part of the compiler. So we have the front end that takes in the source code, generates an abstract syntax tree, checks the syntax, does any sort of semantic analysis, static analysis that we want to do. And then from that abstract syntax tree, we basically do a simple visitor that looks at each part of the AST, each node, and then generates LLVM IR for that node. So if we have a load or a pointer dereference, that would generate a load instruction. If it's on the right hand side, if it's on the left hand side, it will generate a store instruction. That sort of thing. Basically, have a visitor that walks over the AST and just generates code just like you did for Python. So not too complicated there. We're just looking at the AST generating LLVM IR. Once we're in IR, we run this SSA optimization to make sure that everything is in the format that we're expecting, and we generate SSA form LLVM IR then. So then we're in this middle part of the compiler before the backend. So the backend is going to generate assembly code. It's going to handle things like taking that SSA form and figuring out which things do I want to put into registers, which things do I not want to put into registers. It's going to move instructions around when it can, and it will choose what instructions it's going to generate for different parts of that IR, depending on what assembly language you are targeting. So on x86, these instructions look different than they look on ARM, than they look on Spark or some other architecture. So the backend is responsible for that final phase of generating assembly code. In the middle, we basically just have a bunch of passes that start with LLVM IR and end with LLVM IR. And that can be LLVM IR that's had some instructions removed, that has had some instructions reordered, that has changed some values, substituted things here and there. Any sort of optimizations that we might want to perform. So we want to keep in mind, again, that the backend will be doing some of these other tasks, and all of these tasks can be impacted by the optimized IR that gets fed into the backend. So it's basically the optimizer's job to set up the backend for success, that we want to make sure that it's going to be as easy as possible to sort of take that backend code or take that LLVM IR and generate it into assembly code. So first question is, why do we need this optimizer? Is there any reason that we don't just generate optimized code by default from the AST? Or could we generate optimized code by default from the AST? What do we think?
Me?
I can hear you on the phone. I can't hear anything through my headphones.
On the Discord.
I can hear you now, Fish.
Oh, awesome. Why do we need an optimizer?
Yeah, why do we need it? Why can't we just generate optimized code from the AST?
I mean, there's certain operations that don't necessarily need to happen every time, and so I would just say like making the like setting up the program to run faster in advance of actually running it, and we can do some optimizations that will like get rid of things that would be dead code for that run.
Mm-hmm. Yeah, so dead code's a good point there. That we might have things in the AST that seem like we need them, but once we run some other optimization, maybe it turns into dead code. So I think the main point being that like it's it's hard to do this straight from the AST. If we have this setup where we have source code, turn it into an AST, generate optimized code, we need that for every single language, right? Because we probably have slightly different.
Streaming now.
Sorry, what's that?
Oh, this is working now.
Okay.
All right, nice, it's working. All right, there you go.
Okay, cool.
Unmute yourself.
So yeah, if we have this setup where we sort of have AST generating into optimized code, we have to sort of do that process for each language depending on what the AST looks like for that language, and so this may be slightly different for different programming languages, and we can't have these sort of very generic optimizations. So first off, allows generic optimizations. And second off, the sort of bigger point is that what we were talking about with dead code, that often these optimizations sort of play into each other. So there may be opportunities that pop up where we see something that all of a sudden becomes dead code, or we see something that becomes a constant because we were able to optimize some arithmetic expression to generate that constant. So optimizations often feed into each other. And we'll see this in a second here. So we're going to start off sort of by looking at this code here. So this code just takes, sets up a couple defines for the size, generates a couple big arrays in memory and a two-dimensional array in M. We're basically allocating the memory for that up here. This part's not super important. This is the code that we want to optimize. So here we're just going to look at this from a source level, but this is the sort of thing that the compiler would be doing. So if we look at this code here, what are some ways that we could try to optimize this code? Not thinking about it from like an algorithmic standpoint, but from like a what are the like small operations that we could do a little bit faster, or that we could maybe do once instead of multiple times? So first off, let's say like this is a single line. We're going to run this inner loop a bunch of times, right? So we're going to run both loops a bunch of times, but more specifically, we're going to run that inner loop 20,000 times in a row, and we're going to do that 20,000 times. That we run that inner loop 20,000 times in a row.
We need to do the access to x of I every time, like going into the array and finding it every time. I think would waste a lot. So above the inner for loop, we could say set x of I equal to a variable, and then just call that variable every time.
Right. So if we do this, if we have int xval equals x of I, we can replace this because we can see in this inner loop that x of I is actually not something that needs to be recomputed every time we run that loop. So this is what we call loop invariant code motion, meaning that we have something inside of a loop. It is not variable for that loop. It's it's invariant on that loop, and we are going to do code motion by moving that code outside of the loop. This gets abbreviated to LICM, and this can reduce the overhead of this loop, because now instead of going to memory, finding x of I every single time, doing the loads and loads that would have to happen to load that value, now we can do it once, and that happens for every instead of happening in every 20,000 iterations of that inner loop, now it happens once per outer iteration, which is how often we have to change that. Is there anything else we can do that for here?
Could you do it for the M at I as well?
Yeah. Right, so we could do mval is now a pointer, right? But we can also replace mval so that we have this mval of m of I, and now we're only doing the dereference, only doing the lookup for j at this point, so we don't have to worry about what the value was for I. We've already gotten that memory reference, and now we're only accessing this mval every single time through this loop. So this is going to be quite a bit more efficient because we're not doing a bunch of extra loads 20,000 times, especially this one because now we're only really looking up things based on j. So we have 2 memory locations that we're looking at here. There's a lot less chance that we end up running into things in the cache that we might have issues with. Where in a cache we might have 2 things conflicting for the same location. Now we're only accessing 2 different memory locations, so there's a little less chance of that happening. Rather than here where we have this, sort of strided access through X, we have a strided access through a 2-dimensional array. There's a bit more chance that we have things conflicting in the cache running into each other. So what about increasing scope here? So this is a little more complicated of an optimization, so I'll sort of go through this one. But here we're doing, y at j equals y at j plus xval plus mval of j. Nothing here is dependent on the previous iteration of this loop. So you can see that we don't have a dependence from j equals 0 to j equals 1, right? If we wrote this code out, there's nothing that sort of links back from j of 1, or j equals 1 to j equals 0. So since all of these loop iterations are independent, we can do what's called loop unrolling. And that's just going to be to change this loop to do multiple iterations at the same time. So we could loop unroll it to 2. And that means that now instead of doing j++, we're going to move up by 2 every time. And at each j, we're going to do the 2 iterations in sequence here. So we're going to do j, and then we're going to do j+1. We can make this a little more, unrolled if we want to. And we can do j+2, j+3 for both of these as well. And that way, now we're doing 4 iterations of this at a time. And I need to change my plus equals to 4 here. But this is now loop unrolled so that we're doing this 4 times for every loop iteration. So there are a number of benefits here. One of them is that this is probably a little bit better for the instruction cache because now we are sort of, moving the code into a reasonable size that this might fit in a single block, and that other things wouldn't end up in that block. So now when we sort of jump back to the beginning of this code, that's probably in like a reasonable amount of space that it will end up, pushing other things out of that block. So if we end up having other code running at the same time, we don't conflict with things in the instruction cache. What's the other benefit here in terms of the sort of layout of this code for future optimizations? So I guess
Is it going to reduce the? I mean, it's obviously going to reduce the total number of jump calls, I guess, because it's reducing the number of times it's iterating through the for loop. But I'm not sure if that's where you're going with that.
Yeah, that's not where I was looking for, but that is a great point. That it's reducing the total number of jumps that are going to happen. So there are less back edges that we have to follow. Jumps are usually kind of hard for the hardware to handle because we're not sure if they're going to go, which direction they're going to go. So yeah, this is less time that the hardware has to do things like speculate, guess that we're going to go backwards, and then sometimes be wrong. And that used to be pretty cheap, but now that like Spectre and Meltdown have caused hardware people to have to implement defenses against speculation attacks, it's not so cheap now. So yeah, that's a good point. That jumping backwards is going to be a little more expensive, and now we don't have to to do that. I will send out the Kahoot code when we're finished because I have to generate the offline version of it. So I'll send that out as soon as we're done. So what else in terms of the other benefit here is that we have more scope, right? So in terms of the back end of the compiler, it can now see that we are doing 4 of these in a row. So any of the instructions that are here, it can see that we can do all of these at the same time. It can probably analyze that like y at j and y at j plus 1 are different. It may not be able to analyze that m val at j and m val at j plus 1 are different things from y, but that's sort of a different story. But it may be able to figure out basically that like these things are all independent, and so the code that can be generated could possibly be, you know, instead of load, you know, 3 loads, so load times 3 into add times 2 into store, it might end up doing, instead of that, for each of these instructions, it might do load x3 times 4. Like it might make more sense for it to start all of these loads off for every single iteration to make sure it brings everything into registers right away and that we can use those without waiting for them. And then, you know, do add x2 times 4 and then store x4. So it can reorder these instructions because of the fact that we have these all in one scope, that it's in a basic block now, right? We have that single entry, which is the beginning of this iteration of the loop. We have the single exit, which is the looping back or exiting the loop. And so it has this optimization scope that's available to it, that it can decide how to order these instructions in the best way possible in the backend code generator. So this can be really advantageous. Basically, increasing the scope of optimization can allow us to do a lot more effective things once we get to the point that we're scheduling instructions, once we're generating instructions. You know, here, if we have vector instructions on a processor, we could do those loads or stores as a single unit because we know that we're doing 4 loads in a row from the same buffer and 4 stores in a row from the same buffer. So we might be able to generate better instructions in terms of instruction selection. So this is where these optimizations sort of feed into each other, that now we might be able to do other things in order to optimize the code because of the fact that we have more room for optimization, given the fact that we've unrolled this loop. So back to the notes real quick. So this first transformation, we can either do, let's just rewrite this to be the 2 transformations we can perform are loop unrolling and loop invariant code motion. We will get into more of these things. We'll go over a list of all of these common optimizations. We'll look at what is in GCC and LLVM in terms of what do they commonly implement. But the 2 that we're looking at here first are loop unrolling and loop invariant code motion. So benefits of loop unrolling. The first one we talked about is sort of the cache stuff. And the term we'd use for that is spatial locality. So we'll use that term here and there, basically meaning that memory accesses are more likely to fit in the cache. Things are closer together in memory. And due to the way that caches work, they bring in data that's close together in memory. That means that we have better spatial locality and likely faster runtime on an actual machine. And then the indirect benefit from loop unrolling that we just talked about is that they have a larger scope to analyze. So that's sort of the indirect benefit of this is it increases the scope, and that allows us to move things around. And then, of course, we can do the loop invariant code motion that has some benefits as well. So we just talked about possible upsides to this. What about possible downsides? So benefit is the scope. What about downsides? So what would be the problem in terms of thinking about the back end of the compiler? What is going to be harder because of the fact that we unrolled this and now have all of these values that we're maintaining for each iteration of the loop?
I guess more
Application.
assembly instructions are going to be generated.
It's going to generate more assembly instructions probably. So yeah, there is more stuff in this block. There is a point that we will get to where if we unroll this loop too far, like if we did 32 iterations or something like that, we could get to the point that we would have too much to fit in the instruction cache or in like a block in the instruction cache, and then that could be problematic. So the other issue, Mike Sarah pointer aliasing is pointing out is the register allocation, right? So now we have, if we think about this in like SSA form, right, we have y1 equals y1 plus x1 plus m1. We have y2 x1 or x2 m2. So we have 4 different values for each of these arrays that we're probably storing in registers, right? We're loading these values from memory, we're putting them in a register, we're then using those values in this code. So now we have to think a little bit more about where would we put all of these things, right? We have 4 values here, we have 4 values on the left, we have 1 value for x, so we have 9 values total. If we only have 8 registers, that makes this complicated now, because now we have to figure out like which things do we need at which times. We can't now schedule these or generate the code the exact way that we'd want to, the sort of simple way where we generate load, add, store, be able to move things around, because we might have register pressure to the point that we can't actually put all of these values into separate and independent registers. So we kind of have to think about the cost that we might have later on in this optimization process when we get to the point that we do have to fit all of these virtual sort of SSA registers into the real registers that are on our machine. So we have to ensure that we don't sort of overload the back end of the compiler. So downside register allocation and more code. So when we analyze these optimizations, there are a couple things we have to consider. The first one is the sort of most important, which is that we want to ensure that the correctness of the code is preserved. So this can be defined as the safety of the optimization. We want to make sure that when we perform an optimization, we don't ruin the code, right? So this is not too complicated of a concept, but that we have to make sure that when we optimize the code, we don't break it, or we don't break it in a way that is not allowed by the language specification, I should say. So there are cases where we can sort of say it's okay to break this code. And we'll talk about that eventually, that we'll get into sort of undefined behavior in C and C++, where it is possible that an optimization we perform does break code, but due to the fact that the language specification is written the way it is, it's okay for the compiler to break the code in those cases. But generally speaking, we want to make sure that we are conservative with our optimizations to ensure that the optimized code produces the same result and the same side effects as the original unoptimized code. So it's better for us to miss an optimization opportunity due to being conservative rather than produce incorrect code because we did something wrong. Okay. The other two things that we have to consider are closely related, and we've hit on this a little bit already, which is the possible benefit of the optimization. We would consider that the profit. We're going to be a little bit quantitative economics here. And then the possible downside is going to be the risk of the optimization. So we want to basically figure out, is this optimization going to be worth it for us to perform in the event that there are some possible downsides. So when we're thinking about loop unrolling or loop invariant code motion, loop unrolling, the benefit is the scope. We have to know whether the profit of increasing that scope is going to outweigh the downside of having more problems with register allocation and possibly having more code that doesn't fit as well in the instruction cache. So we want to try to analyze it to see, is this optimization going to be beneficial or not? Okay. Okay, so before we move on, let's just talk about a couple other things here. So there are a couple common cases in which we can apply optimizations. The first one would be reducing the overhead of an abstraction. So what can we think about in terms of C++ abstractions that we might want to reduce the overhead of? Anything that's expensive in C++ that we might want to make it perform a little bit better. What can we think of here?
Would that just be defining classes?
Classes? Yeah. Right, so classes are a really nice abstraction. They add a lot of additional overhead, right, if we don't reduce this. So things like just methods in general, the this pointer, if we go into something like virtual methods, inheritance, all of this stuff is, are cases where we may want to reduce the overhead of an abstraction. So like virtual methods, these are, we call into the sort of v pointer, or we look at the v table or look at the v pointer. We use that to reference the v table. We then look up the method that we're going to call, and we call that method. Are there cases that we can reduce that? Can we inline some methods? Yeah. So like, let's say I have a virtual method here, but I can look at the code and 100% tell that this is going to call this particular method statically. I can 100% guarantee that it's going to go to this particular method based on the analysis that I've done. So we could, basically take advantage of special cases where we say, given conservative static analysis, turn virtual method call into static method call. Right, so that would be a special case where we can sort of check and see, hey, there is a particular use case here that we can, translate this into something else. Other special cases would be things like I know that I'm operating on, for example, like strings or characters. There may be special instructions for handling characters and doing things with them, like moving them around in the system. Special data types. There might be special instructions that we can use to manipulate them, or cases where, like, I know that there is going to be a character used here in this data type instead of something else, or I have a template that I can specialize. Oh, is everyone else having this? Is everyone else having rendering issues?
I'm able to see it.
Okay.
Yeah, I can see it.
I will be posting it to YouTube though. You can't see it either. Okay. Let me see if there's anything I can change here. And try restarting it and see if it fixes it. Can you two see it now?
I can see it fine. Oh wait, yeah, guys, just left.
Still nothing, Fish? Yeah, I will definitely post it to YouTube whenever we're done. Okay. Okay, it's showing 6 viewers now, so see if we can get it back up. Has Hangouts been working okay?
I'm using Hangouts for another class and it works pretty okay.
Okay, maybe we'll switch to that because I was trying to avoid it. I didn't know if it'd be able to handle the load, but yeah, if it's working better, then maybe we'll switch to that for next class. Though we should still, I did want to mention we should be using this tomorrow because we can't use video streams while we work on labs due to the VPN connection. So let's just finish up talking about this and then some logistic stuff here. In any case, so final thing here, optimization case is matching code to system resources. So this one is the case that we know the size of the cache lines, we know the layout of the system resources, or we can kind of guess in general what machines are like. So at this level, we may not always know what this is going to be or what the actual system implementation is going to look like, but we can make a guess, that it's going to have some sort of a cache, and if it doesn't, it's just going to be slower anyways. So we can try to do things like basically, add padding in class layouts. So we can set up the layout of a class member so that we have enough padding to make sure that each one fits appropriately into a cache line. So that way we don't have interference between things in our programs. We don't have issues with basically this setup where we have too much space or too little space being used for a data member. So we may match code that way. We may change the size of arrays. We may lay out things differently. We may access things in different orders depending on how we expect the system to use them. But this is sort of the final case here. So any questions so far on this material? We'll get into specific optimization scopes and things like that starting on Wednesday. So just for the rest of this, I just wanted to chat about, I'm going to end the recording here.